When we're looking at Unit 4 of AP Statistics, most of the unit is talking about probability and random variables, and you just need knowledge and maybe some basic calculator usage in order to do all that. But for the binomial and geometric distributions, there are calculator functions that you will need to know, and if you're using Desmos, you're going to have to know how to do it on this calculator. I'll very quickly go over the specific functions in Desmos, and then I will go over some more details and about each of these distributions and some knowledge from that can be good review. First, for the binomial distribution, if you type in binomial dist and then you put in your number of trials, I'll go with 10, and your probability of success, say 0.75, you can then zoom fit to have the PDF appear on your screen. And here it is. You can click on any one of these dots and you will be given an ordered pair here where you have the x value and your y value is the probability of that many successes given these n trials and these p probability of success for each trial. Then you can go into the cumulative probability tab. This is your CDF. You have a lot of options here, inner, outer, left, and right tails. Make sure when you are using this that you are aware that this is less than or equal to, or in the right tail, it's greater than or equal to. So if a question is asking, in this case, less than or equal to 8, if it's saying, what's the probability of getting less than 8 successes? This is not less than 8 successes. This is less than or equal to. This includes 8. If you actually check the graph here, you can see that this is filled in, and there's that line there, and all that probability here is being counted. So if you want to be less than 8, you're going to do less than or equal to 7. This is a problem that only happens in discrete ones, like binomial and geometric, and not continuous distributions, like the normal distribution, but you always have to be aware of it whenever you're inputting this, or you will get the wrong answer. Next, we have the geometric distribution. You'll type in geodist of your probability, let's say 0.25. And this is going to work basically exactly the same as binomial distribution. It is also a discrete continuous variable. It is defined on integers from 1 all the way to infinity, which does make it a little bit different, but again, the sum does add up to 1. It is still a valid PDF. You can still click on each of these dots here to see the x value and the corresponding probability of, again, geometric. This is how many trials it takes for the first success, although if you go far over here, it'll be rounded down. Eventually, it'll be rounded down to 0. So then you won't get much knowledge. And then you can use the cumulative probability tab. This is the CDF, the geometric distribution, and this is going to work exact same. Left tails, right tails, similar to normal distribution and binomial distribution. And again, this is discrete, so be very aware if it's greater than or equal to. Always double check whenever you're using this function and making sure you're doing this correctly. Another thing, if you don't want to type this out, you can go up here to add item. This is for either of them. Go to inference, this and then probability distribution. You can choose right here, binomial and geometric are here. You can put in your trials and your probability of success, and that will pop up for you. You can also go into the keypad tab, to functions, and under probability functions, they will have all of these functions, and so you can click those and it'll automatically just pop up. It defaults to 0.5 probability, but you can put in anything you want there, and then you can answer your question like that. Now that I've gone through that, I'm going to go into a little more detail into each of these distributions. First, the binomial distribution. Here we will say x is distributed as a binomial with n trials and probability of success p. And what this means, looking at our PDF here, is that the probability that our distribution equals x, or x successes, is here we have p to the x, which is the probability of getting x successes, and 1 minus p times, or this is times 1 minus p to the n minus x, which is the probability of getting n minus x failures. But this includes all the different combinations of getting p successes, or sorry, x successes and n minus x failures. So this binomial coefficient adds all of them together. This is number of combinations of x successes and n minus x failures. We can you can use this function. This is more Desmos way to put it. The binomial coefficient is written as NCR of an n and x. And you can graph this here. This is the same thing. And what I'd like to show you, a few things. One, the mean is n minus p. And this is something you have to memorize, but it's pretty easy to understand, pretty intuitive. Um, if you are doing 10 coin flips, which is kind of what this example shows, you'd expect it to be around 5. The true mean, you'd say, like the population mean, would be 5 coin flips. If you were to do this many different binomials, the average of all these binomial trials would be 5. And what's good to note, especially when you get into weirder like n or p values, like if you go around here, um, the median and the mode are almost always going to be the nearest integer to your mean. So you would just round this down to 5. You can see that is the mode, that is higher than 4, and I believe it would be the median too. And you would check with the CDF though, which you could do with the CDF tab. And then also, I would like to show, when you're moving this p-value, you can see the distribution moving, and you can see when you get into high values, and when you get into low values, the distribution becomes highly centered in a few values. And you can actually numerically see this in the standard deviation. If we look at this equation here, it's the square root of np1 minus p, or npq. Now, n is constant here, but p times 1 minus p, or pq, is going to have a maximum at 0.5. It's quadratic, the maximum is there, and that means that our standard deviation is also going to have a maximum of 0.5, which is why we see the most spread here. And then finally, you can also see, especially when it's around 0.5, but also when you increase the n, you'll see it more. Binomial can be roughly normal. This looks kind of like a normal distribution, and as you scale up to higher n values, and especially if you're relatively, in this kind of middle range of p-values, you can actually approximate the binomial distribution as the normal distribution. There are a few use cases for that, and it's very cool. And now I'll just talking about the geometric a little bit. You can say variable x is distributed as a geometric distribution with a probability of p. And this is going to mean that the probability of your first success being on trial x is going to be equal to p as 1 minus p to the x minus 1. What is this? You need to get a success, so that's why p is here, and then you need to get x minus 1 failures. So if your first success is on trial 10, then you're getting 1 success, which is your 10th trial, and then 9 failures in a row. And this is almost a form, well, it is a form, it's a special case of the binomial distribution where x is always 1 and your n is changing. Your n, it kind of is now our x, because there's always going to be 1 success and it's always going to be the last one. Now looking at this a little more, here I have a case of this. Our mean is going to be 1 over p. This also is pretty intuitive because you can kind of think, if I have a 10% chance of winning, you're going to expect to be around the 10th time. On average, it's going to take 10 tries to get it. 1% chance of success, around 100 tries. Your average is 100 tries. And then we have the standard deviation here. When you kind of just got to commit to memory, it's the square root of 1 minus p, or the square root of q, of course, divided by p. And it's just very important with this one to not bring the square root down. Do not write the square root of 1 minus p over p. This is wrong. The variance is actually written 1 minus p over p squared. And so when you square root the variance to get the standard deviation, this square root cancels out the square here, which is why you're left with this. So very important. Do not mess that up.